Hey there, guys. It's Mr. Sheelan here. This is going to be the video covering Unit 5.1 notes concerning momentum and impulse. Now, before we get into it, for the 5 millionth time, there it is. Okay, my toolbar wasn't there off to the left, so let's try that again. Okay, so this is just going to be the notes. It's just going to be me reading through them, giving you some supplemental idea or material to add to your notes. The Check Your Understandings will be in a separate video where all the answers to the calculations will be found there. So let's go ahead and get just right to it. So Unit 5.1 notes concerning momentum and impulse. Fun stuff, guys. Fun stuff. So what is momentum? Well, let's think about how it is described. So momentum typically, as we talk about like in sports, mostly, we talk about how a team has momentum if they're on a roll or if they're hard to stop. It's the idea that in this case it's more of the metaphorical idea that they've got a forward motion that is going to be really difficult to stop. It's described in this case in this metaphorical way that it's as if the team has accrued or all of its happy ideas or at least strong convictions of that moment are increasing, and it's going to be really, really hard to stop them. And the same thing actually applies for the most part to when we actually talk about momentum. When you have a great amount of mass moving at a speed, you need to have a whole lot of energy in order to stop it. And we can measure how much momentum something has depending upon its mass and also its velocity. So this Bill Nye video, obviously I can't show this to you just because it won't record this won't record the audio coming from the video. So I will post this on Google Classroom on the notes post. And it will also be available here in the slides for you anyway. So you can find it in those two locations. He just goes through using bowling as an example of how we use momentum, where it's seen, and what we can do with it. Don't play that. I don't want you to do that. So you probably did hear the audio, probably crap audio, but just ignore that again. I'll post that for you. So in physics, momentum is a vector quantity that describes the motion of a mass. So this we should have known from the assignment that you did the other day. It's a vector quantity, so it does have direction. Now, the only thing is what is that direction? So in this example, or these two picture examples here, so we've got these runners here, right? So we do have these runners here. They're moving in this direction, okay? So what direction is their momentum? Well, their momentum obviously has to be in the same direction, okay? So even if you do have some sort of friction force opposing or slowing down an object, its momentum is still in the direction of motion. So let's take a look here at this boat. Maybe this is the better example here. So we've got this boat, but let's say they turned off the engines right at this particular moment, and it begins to glide and slow down because the engines are off. The motor's not running. It's not propelling it forward. So which direction, if the engines are turned off, is the momentum, or which direction is the momentum moving if the engines are turned off and there's no longer a force pushing it in the direction of its motion? What would it be? Well, it's still moving in this direction. The momentum is still in the same direction as the movement. Okay. Even if you have an opposing force, in this case friction, pushing against this boat, you'd still have momentum moving in the direction as the object. Okay. So it's an important idea to think about, and an important idea to consider that again, no matter what, and I'll draw it again, your boat is moving in this direction, but there's also an opposing force in the form of friction in this direction. Here, we'll make that kind of purplish pink. There's a friction force in this direction, but the momentum, the P, is still in the same direction as the motion, okay? Every time. And then so obviously if you don't have motion, you don't have momentum, okay? Which I think should be touched on somewhere in here, but okay. So an object's momentum depends on its mass and how fast it's moving. Okay, which again, we should remember that from the reading the other day. So if a truck is traveling 5 kilometers per hour, or if or a truck traveling at 5 kilometers per hour has more momentum than a smart car at the same speed because it's harder to stop. There's more mass. Okay, you've got more mass here than you do here. Okay, and this higher mass from this big old truck will provide a higher amount of momentum than this car, which means that this big old truck is more difficult to stop. It's the reason why trains take virtually, or depending upon the speed, but a lot of times, cruising speeds, I guess, or at least I've been told that like on cruising speeds of trains, it takes like a mile for them to come to a stop. Why? Because it's think about it. If you've got, say, 50 train cars filled with stuff, it's going to take a long time to reduce that velocity to zero. A long time. So that's why at train, at tracks, at cross tracks, there's a better word for that. Crossroads, cross tracks, I can't remember. But at those points, that's why buses always have to, stop and try to listen, because if there's a case where a bus stops or a bus is like stuck on there, or any car that's stuck on the tracks, and there's a train coming, you just leave, because there's absolutely no way that train's going to stop. There's just no way. Now, obviously, it, again, depends upon how many cars, but do you really want to take the chance and and think like, oh, well, there's only 2 or 3 cars on that train, I'll be fine. It'll stop and I'll be just fine. Yeah, don't take those odds. So because, again, the momentum the train has due to its velocity and its mass is too great, and it'll take too much energy and too much force in order to stop it before it hits you. Okay. So momentum and inertia. So remember, inertia is the tendency for an object to keep doing what it's doing. This is Newton's first law of motion. Okay. The momentum of an object is the quantification of its inertia. Okay, that's what we're doing here. We are now taking the first law of Newton's here, and we are now more or less quantifying it. We are saying, here is how fast this mass is going, and it needs to be stopped by X amount of force over this span of time, which we'll get to in just a second, because that's the other thing we'll talk about. So the momentum of an object is the quantification of its inertia and how difficult it is to stop its inertial movement. And this is how we quantify it. So it's going to be the P is equal to mass times velocity, which we've pretty much already talked about. Now, this is specifically linear momentum. And I know some of you may have picked up a little bit on angular momentum. Angular momentum is something that we really don't cover in here. It's really getting into some decently advanced physics, so we just really don't cover it in here. It may be mentioned here or there, but as far as calculations are concerned, we're going to just keep it simple. We're going to keep it to linear momentum. Okay, and linear momentum is shown in this calculation. It's P, which is equal to momentum, is equal to mass times velocity. Okay. So here you have some questions. So where M is the mass in kilograms, V is the velocity in meters per second. So what are the units? And actually, I think this is a check your understanding, but just to write it out. So what are the units then? Well, simply put, the units here are just going to be kilograms per kilograms by meters per second. Okay, so it's kg dot m over s. Okay, which is really, really similar to a very particular kind of units that we've already talked about, which is the units for force. It's super close to newtons. But remember, don't get confused. This is momentum. Newtons is kg dot m divided by s squared. Because remember, it's the mass times acceleration. That is the second law of, or the Newton's second law of motion that describes, a Newton. So don't get them confused. If I ask for momentum, the units I need are kg, and realistically speaking, kg and then like x or the asterisk symbol, and then m divided by s is just fine. Okay. If you have to type it out, I guess is what I'm saying there. Oop, I need to. So momentum is a vector quantity, so direction is important. Again, this was mentioned in the reading that you did already. It is super important. So when we write out our answers, that means that you have to associate a direction in your answer. I will take points off if you do not associate a direction, just like when we were going over velocity, when we were going over acceleration, when we were going over angular velocity, angular motion, projectile motion, all of that good stuff. You need to have a direction. Okay. So make sure you put down a direction. Here is check your understanding number one. Like I said, this will be in a separate video. And number two. So let's get into impulse now. So real quick, just on your own, look at this. So which one is most likely to break? Now, this image right here. So this one over here, this is a plate that's going to be dropped on cement. Like this guy right here, that's cement. Say it's just a cement pad, a pre-poured cement pad. Okay, where this guy over here, that is a pillow. So the question is, which one is more likely to break? Which one is the most likely, or which plate has the highest probability of breaking? Okay. So clearly it's this one, right? It's the one that's going to hit the the cement. Now, why? Why is it more likely that the plate will break hitting the cement than it is hitting a pillow? Well, clearly it's because, well, Mr. Sheeline, that's easy. The cement is much harder than a pillow is, which exactly right. Yeah, that's 100% correct. The cement is way harder. What implications does that have, that the cement is harder than a pillow? How else could you describe it without saying, the hardness or the how dense the material is? How do you describe then the reason why the plate will break on the cement? Okay. Well, that's what impulse is. Impulse is the force the force and the time needed to bring the momentum of an object to a stop. So you would say that, well, the impulse from the concrete is virtually zero. Okay. So because it's nothing, because more or less as soon as the plate hits this concrete, there is no time that a force is being applied. It's instantaneous. Whereas on the pillow, okay, it has a couple of milliseconds. It's got a little tenths of a second where it takes until it settles, right? Think about it. If you drop something on your pillow, okay, it actually kind of squishes through the pillow. It doesn't, the pillow doesn't just break your plate, unless you've got a really, really hard pillow, I guess. But the idea is that the impulse is the amount of time that a force can be applied onto an object in order to change the momentum. Okay. So let's take a look at that. And that's more or less what I'd be looking for here. It's that. So looking at Newton's second law, we can derive the impulse equation from Newton's second law. So here we have, the sum of forces, the net force is equal to mass times acceleration. So then what we do is that we break down acceleration into velocities. We move time over and we multiply that on both sides. We get it over with the net force. And then what we do right here is that we then factor in the mass to the velocity, final velocity, and the initial velocity, which then brings us to this down here, which then just translates into final momentum minus initial momentum, which can be just translated into the change in momentum. Okay, so we're going to be bringing back ideas of final and initial velocity here. Okay, so here again, this is our impulse. This is your impulse equation. And again, impulse, and this should be on the next slide, but impulse, the change in is the change in your velocity is equal to the amount of force and the amount of time that force is being applied against that momentum. Okay. Oh, for goodness sake. Come on. Jeez. Sorry. So there it is again. So impulse is a force acting for a given amount of time to change an object's momentum. Okay. Its direction is the same as the change in momentum. Okay. So in the case of, let's see here. In the case of, let's say, the airbag dummy here. So the airbag dummy, okay, let's say it's moving in the car. It's moving in this direction, okay, because the car was moving in that direction. So its momentum is moving in this direction. Now, the impulse, though, impulse is more or less translated through the airbag, because that's what the airbag is designed to do. It is to reduce the momentum. It is a force that is produced to reduce the momentum of a moving body, in this case, the dummy, but it's in this direction. Okay, so the impulse, which again, the impulse here, I'll just write out impulse. The impulse here, which is the change in the momentum, the impulse is in the direction of the green arrow, while momentum is in the direction of the red arrow. Okay, so its direction is the same in the change of momentum. Okay, now does that mean it's always opposite? No, it doesn't mean it's always opposite, and we'll see that when we get to more into collisions. But just so keep that in mind. Okay, but for the most part, it's in the same direction as just the change, generally speaking, because it can happen at angles, which we'll see when we get to collisions. Okay. So here is the equation. So it is equal to an object's change in momentum, which we understand. If you increase time, though, the net force will decrease. Okay, it will decrease. So if you're trying to catch a ball and you move your hands back with the ball, as it approaches, you will increase the time needed to stop the momentum. Thus, you're decreasing the force required in order to stop it, which means it hurts less. It's the same thing as what we're going to talk about here, the importance of follow through. It's why it is that athletes are told, both with throwing, with you could say with basketball, not so much here. And what's not pictured here is the opposite end of this guy, the batter. You want to follow through with your shots when it comes to in baseball, when it comes to tennis, when it comes to golf. The idea is that the longer that your club, the longer that your racket, the longer that your bat is in contact with the ball or whatever kind of object you are trying to alter, you're trying to change here, the less force and the better chance it is that you're going to change its momentum. So in the case for baseball, you're going to have a ball thrown at you, and instead of just kind of whacking it, okay, and not following through, which I will tell you from personal experience, hurts more than you can believe, like basically hurts your arms, your forearms, your shoulders, can really, and you can really actually hurt yourself by not really doing that. And that's why I don't really recommend that you try to hit a ball traveling, at 80 miles an hour, which is nowhere near pro level speeds. But again, you want to follow through because you're trying to increase the time that your racket, your club, your bat has with, in this case, a golf ball, a tennis ball, and a baseball. Okay. Because you want to change its direction, but at the same time, you want to do it as efficiently as possible. Okay. It's the same thing in boxing too. You want to ride the punch. So it's why you try to catch your opponents flat-footed, is because when your opponent's flat-footed, they have there's a less degree that they, or a lesser chance that they have in order to kind of maneuver either away from a punch or at least to absorb the blow a little bit. It's the idea of you moving with the punch. It's riding the punch. You are increasing the time that in this case, the boxing mitt is meeting whatever part of your body, but that meat that you riding it means that there's an increase in time that it's in contact with you, which means there's less of a force that's affecting you at that exact moment. And as you can see here, that's what they show. That's what they're showing in these. So here is where you're riding it, and then here is where you are just taking it like hard. Okay. The idea is that as you increase the time, you're decreasing the force. Notice the little F versus the big T. Now that's polar opposite. If you decrease the time, okay. So decrease the time, you are increasing the force. Okay. You don't want to, if you're in boxing, that's why that is something you train for. You not only train for just avoiding punches, because it's inevitable that you will be punched. You've got to know how to take a punch. And this is what they're talking about. It's riding the punch. So it says down here at the bottom, riding the punch, increasing the time of collision and reduces the force of collision. Okay. So I know, and again, I know that seems weird. But just continually think about it. But again, and hopefully this one is the this is what really helps you understand this whole boxing idea that yeah, if you're going to get hit, you want to increase the time of collision, because the increase of time in collision means that you have less force. Realistically speaking, it's not that there's a less force. You just there's more of a distribution of force across the body. It's that's what it more or less is. It's not so much that all of a sudden you're magically changing the magnitude of a force hitting you. You're just you're displacing it differently is what you're doing specifically. Okay. So, and it's like these little pads that you have on walls in the gyms. If you've never ever thought about what those are for, if you thought they were just or decorative pieces, nope. Those guys are foam pads there for a reason. Now maybe you already knew that, and maybe this is, and especially since you're juniors and seniors, that you already understood that. But this is specifically what it's there for. It's to increase your time in contact with the wall in order to distribute the force that you're applying to the wall. So if you are playing dodgeball in the gym and you're running a home plate like mad, but you have because of your mass and velocity, you have a real tough time slowing down. And you know that if you slow down too quick, that you're going to hurt yourself either by tripping or sliding and skidding across the floor, or who knows, even something worse than that, like breaking bones. Here you can slowly alter your momentum, slowing yourself down, and if you need to, you can slam into the wall relatively, at a relative pace, because it's not to say that this cushions your blow completely, but it does cushion it enough to where it doesn't, you will be better off than you were if they weren't there. I guess I'll just say that. Funny story is I played basketball in 8th grade with a kid that did punch like a pillar in our middle school with a pad on it, and he thought that it was going to be enough to he thought it was going to be enough padding to cushion the blow. He punched it and then broke his hand. So and I mean not just breaking it, where your hand meets, like he broke it there, and he broke some of his fingers too. I don't recommend it because again, they are not designed to completely, cushion the blow. It's not like those big inflatable bags that stunt doubles jump onto, when they're jumping from buildings for movies. It's maybe 1.5 inches of foam, maybe 2 inches of foam. It doesn't protect you from that much, but still, it's still more than nothing. And of course, airbags, This is exactly what they're designed for. It is to change your momentum. And then a couple more check your understandings, and that's the end of the notes. So, okay. So again, the check your understandings are going to be in a separate video. So make sure you go watch that and see what the follow through is there, and see if you get the right answers over there. That is the end of the video, guys. Thanks for watching, and I will see you in the next one. If I can remember, that's it. Yep, there. See ya.